Okay, so today I'm going to discuss about uncertainty measurement. This is kind of review in relation to ME 324 course, Mechanics of Materials. For some of you who has already taken course, this is kind of review. And for some of you who has not taken this course, I think this video may help you. Okay, so it's more related with the calculation of repeatability, which is measured in terms of covariance, and also if you want to calculate uncertainty due to propagation of error, this video can help you. So here we talk about standard deviation, so what standard deviation is and what mean is, and then we talk about repeatability, because once you take the data we have to know whether um, your data is kind of repeatable or not. And also we'll talk about different kind of uncertainty, so that's what our focus will be on. So standard deviation, so you may have data, maybe you take data in the lab, maybe you are measuring volumetric flow rate, maybe 1 meter cube per second, and then 2 meter cube per second, and then 1.5 meter cube per second, 1.4 meter cube per second. So you take number of data, and if you add together and divide by the number of data you have, so if you add all together and divide by 4, that would give you um, the mean. So this is the mean. And then um, standard deviation is, like, for instance, for this distribution, this is the mean. Sometime if it is for the population, you write by mu. If it is for the sample, you write by x bar. And so is the case for standard deviation. This is for population and this is for the sample. So the standard deviation is how much deviation you have from the mean. So here any variable of flow rate in this case, and then minus mean, and then you do for each one of these variable. So this should give you how much is the spread of this data, which you call as a standard deviation. Okay, you may see sometime divided by n. If it is just divided by n instead of n minus 1, it is for the that is the standard deviation of the population. And usually if it is for the sample, you see it is divided by n minus 1, so where n is the number of sample. Okay, so that's the meaning of standard deviation. And if it is a normal distribution, then within plus minus 1 standard deviation you have like almost 68% of probability. Minus 2 sigma to plus 2 sigma, you have almost 95% um, of your data. And then if it is between minus 3 sigma to plus 3 sigma, you have almost 99.9% of the data in between that. So this holds true for distribution, which we call as normal distribution. So the key point is here, you should know how to find the mean, you should know how to find the standard deviation, so that is important to us. Next I'm discussing about the repeatability. Repeatability means, like, again, the same thing. You are, let's say, making the measurement, and you are making the measurement of the flow rate. So you took the reading, like, again, 1 meter cube per second. Again, you took the reading 1.1 meter cube per second. Maybe you got 1.5 meter cube per second. You are taking the measurement of the same thing here, okay, but at a regular interval. So for this one, so you took many number of reading, and you want to find whether these data are repeatable or not. So every time you are taking the reading for the same thing with the same equipment, you should get pretty close value. And if you are getting value different, then you don't have a good repeatability. And in order to measure repeatability, which you'll be doing in your lab as well, you measure through what you call as the covariance. And covariance can be measured by this. So you have a standard deviation, which we know before, and then mean of the sample. So basically, if you have some kind of distribution, so this is kind of mean, and how much variation, how much spread you have. So the ratio between these two is a measure of repeatability. So lower this value, lower the value, and if you multiply it by 100, it would give you in percentage. So lower the value of this one, the more repeatable your data is. So that's how you make a measurement and you make your judgment. You are the one to tell whether it is repeatable or not. So you could have some criteria. Maybe if you get 5% or 10%, we can consider to be repeatable, and accordingly you can make your decision. So that's how you measure repeatability, which is a covariance and is ratio of standard deviations divided by the mean of the sample. So this is an example. Again, here this is a measurement flow rate where we are trying to measure the repeatability. Okay, so you have this 1 2 3 4 5 data of flow rate. Now we want to see whether this whatever data you have is repeatable or not. So again, in order to find whether it's repeatable or not, you need to find the ratio between the standard deviation and the mean of the sample. And sometimes you'll also see, if it's a sample, instead of sigma, you'll see sample standard deviation by the mean of the sample. So for this data, you need to calculate the mean. So mean is just add together and divide by number of data, which is this much. And for calculating here is denoted by S, which is the standard deviation for the sample. So use the previous formula. So you find the deviation for each one of these, and then if you use that formula, again for sample you have n minus 1, so you get this value. And in order to find the covariance, so you have this standard deviation of the sample and divided by the mean. So the mean, so you have, and if you multiply it by 100, it would give you in percentage. So the variation, it's just 0.68%. So that means it's not very. So if this is mean, just very small variation. So you could say that the data you have is highly repeatable. So you are getting the reading very close to the mean value. So that's how you can say, based on the value of covariance, the data are very much repeatable. So covariance, excellent repeatability, scatter is less than 1% of the mean. So flow measurement are consistent, reliable. So that's how you make your decision in relation to the covariance. Okay, next is we are moving on to error and uncertainty. Okay, so our goal is to calculate uncertainty, and you may have in mind, why not error? So when you think of error, error is defined as measured value minus the true value. So maybe again we are making measurement of flow rate, liter per minute or meter cube per second, right? Flow rate, but we never know this true value. This is very hard to find. That's why it's very difficult to calculate the error. So you get the measurement, but it's very hard to find the true value. So there is kind of practical difficulty in finding the error because we don't know the true value. Okay, so that is why we need to go for calculation of uncertainty. And uncertainty is kind of quantification of doubt related to value. So how much variation you could have when you make the measurement. So that's what uncertainty. So that is the reason why instead of calculating error, we go for calculation of uncertainty. Okay, so you have measurement and calculation uncertainty. So it is described by interval and confidence. So you may say at 68% confidence, you have this is the mean value and this is the uncertainty at 68 confidence. If the confidence is high, the uncertainty value will also go high. So you have 99% confidence, so your temperature could be, so this is the value of uncertainty. Okay, so we are interested in calculating uncertainty, not error, because it's hard to know the true value when you make the measurement. Okay. So in relation to error, you have random error. As the name suggests, random means it's random, so it's very unpredictable. So you are taking the measurement, you took the measurement again, flow rate, let's say 1.5 meter cube per second, and then again for the same thing you make the measurement and you are getting 1.4 meter cube per second. See, you are making the measurement with the same instrumentation, same place, at different time you are getting the different value. So what is the reason? So we don't know, it's very unpredictable. It could be due to environmental factor, maybe temperature, pressure is changing, maybe variation in procedure. So it's very random in nature, okay? And this can be reduced by increasing the number sample size, maybe averaging the data. So we call that as a random error. There could be another type of error as well, which is a systematic error. Systematic error is unidirection. For instance, if you are making a measurement, if there is some kind of offset of, let's say, if you vernier caliper, always 0.1 millimeter offset, right? So if you have offset, always this error will be there. That's called systematic error. You may have some kind of observation error as well, like imperfect instrument calibration. So when you do the calibration, you may have error as well. So which is kind of constant every time you take the measurement, unlike random error. So anything other than random is a systematic error, and it can be reduced by calibrating equipment, using controlling experiments. So these are called the systematic error. Now we want to find the uncertainty associated with the random error and systematic error, and we call that as type A and type B measurement uncertainty, and this type A is related with the random error. So whatever the uncertainty associated with the random error is called type A uncertainty. So usually, if you want to calculate the type A uncertainty, which is associated with the random error, so this is given by, this is complicated, but this is just an example, by standard deviation divided by the number of sample. So this is at 68% confidence. In order to calculate the exact value, it's very complicated. So for our lab ME312, we usually don't calculate this one unless stated. So we'll focus on type B uncertainty, but it is very much kind of complicated. But if required, we will be using this formula, standard deviation. We know how to calculate the standard deviation of the sample divided by the number of sample. That would give you the measure of the type A uncertainty at 68% confidence. If it is at 95%, this is going to change. So we will be doing everything for this lab at 68% confidence. Now type B uncertainty measurement is related with the systematic error. So type A related with the random error, and this one is related with the systematic error. Okay. So how do you calculate that? Again, when you talk about type B measurement uncertainty, it could be due to various reasons. One of the thing which we'll be doing in this lab is we'll try to calculate the type B uncertainty based on resolution. I'll show you example where you have also type B uncertainty due to calibration or some other thing, but here our focus in this lab will be on calculating the B type uncertainty based on resolution. So if you have an instrument, vernier caliper or mass measuring instrument, if the uncertainty, if the resolution is like, let's say 0.5 kg for mass measurement, then your uncertainty B type would be resolution divided by 2 and then square root 3. So this is how you calculate, and this is only the thing we'll be calculating for the lab. So if you simplify this one, they should be given by resolution. So if you write inside this one, so 2 can be written as here 4 and then 3, so it becomes resolution divided by square root of 12. So you may see this formula, or sometimes you may see this as well. It's the same thing. Okay, it's the same thing. So this is only the formula which we'll be using to calculate the B type uncertainty for our lab. And again, it is based on resolution. There will be other factor as well, but we don't take into account in general unless stated for calculating the uncertainty. So I can show you the example. For instance, again, you are trying to measure mass. Okay, you are trying to measure the mass of this one. So you have mass, and then there is always a resolution associated with the instrumentation. So we have in our lab as well. This is required. This type of calculation is required. So we are trying to calculate the um, B-type uncertainty at 68 confidence based on only resolution. Okay, and the resolution is this one. Now we know the uncertainty associated with the mass based on resolution is resolution divided by 2 and then square root 3, or it is same as resolution divided by square root of 12. The same formula. This is plus minus. So it's the same thing, resolution 2, and then so this is the uncertainty, B-type uncertainty based on resolution. So this type of calculation you have to do in the lab. I think we are doing for any instrumentation that you use. So you're at 68% confidence. So this is the mass, and then on B-type uncertainty is this value which you get from here. So this is how you calculate the uncertainty associated with the variable that you are measuring. You could do for length as well if you are measuring length. So you have vernier caliper. So in that case, again, if you take only resolution, so resolution divided by 2 and then square root, which is square root 12, and that would give you the uncertainty, which is B-type uncertainty plus minus. So this is how you calculate. But the uncertainty in B type could be due to not just the resolution, it could be any other factor as well. So like it could be due to error provided by the manufacturer. It may say 5% error. It could be due to linearity, it could be due to repeatability. So these are all the type of B type of error. Now if you want to find out the average, total value, then we use what we call as RMS method. So which is the maybe due to resolution, this is the value square, and then due to linearity, this is the uncertainty value, and you can have due to repeatability, you just square it and add together and take the square value. That is why it is called RMS value. So this is how you calculate the B type of uncertainty value based on RMS if you have many factors that contributes to B type uncertainty. But in our lab course, we are mostly focused only on resolution unless stated. So just do the previous method. But if you have many, like these examples, you have, again, you are measuring a mass and you have a source of uncertainty. One is due to resolution. So again, you follow the same method like here, 2 root 3 or square root 12. And this is related with the uncertainty for the resolution. You have a manufacturer tolerance. This is the plus minus. Again, this is for uniform distribution, and this is the formula. So you are getting uncertainty due to manufacturer tolerance, and this is due to calibration. Now you are trying to find the average value, which is you are using root square method. So you take the square, add together, and take the square root, and this is the overall uncertainty B type if you have many sources of uncertainty. And this is so the mass, this is the uncertainty B type value. Again, for our case in the lab, we may be focusing only on the resolution, so you don't have to do all three. But in case if you have many factors that contributes to B type uncertainty, then definitely you have to follow this way. Okay, now we talked about uncertainty associated with the random error, which is A type uncertainty, and this one is the uncertainty associated with the systematic error, which is UB. Again, it can have many factors as well. If you want to find the total uncertainty, so you have to do UA square plus UB square, and this can have also you can use RSS value as well. The one which I showed was based on 68% confidence levels, where we call coverage factor K. If you want to increase the confidence level, then you need to multiply this by 2. K is 2. If you want to increase to 99%, then you need to multiply this by 3. But again, in our lab, we are doing everything on 68%, so you don't have to multiply either by 2 or 3. But in case If you want to increase the confidence level, you can always multiply this coverage factor. Okay, now the big questions. So we are measuring just mass, okay, just mass, and just one variable we are able to make the measurement, and we didn't talk about propagation of error. Okay, and the question is when we need to use the propagation of error, right? um, so for instance, if you want to find density of some fluid here, if you want to find the density, can you measure the density directly? No, density is mass per unit volume. So in order to measure density, you make measurement of mass, you make measurement of volume, and once you know this one, only we know density. This is a derived quantity. You don't measure it directly. So this is a derived quantity which depends on the measurement of mass and volume. So in this case, density is a function of two variables. And we are measuring based on the measurement of mass and volume. We are not measuring this directly. So this is a derived variable. So in that case, whatever the error associated with the mass and volume will propagate to density. So that's why in that case we have to use the propagation of error uncertainty analysis. In the previous case, if you are just measuring mass, just single variable, then you don't have to use the propagation of error. But if you are measuring density, you cannot do it directly. You have to measure this one, you need to measure this one. So whatever the error here propagates to this one, right? So that is why if you have a variable which you want to find the uncertainty, and if it is a function of measurement of more than one variable, then like density is a function of mass measurement and volume measurement, so in that case you have to use the propagation of error uncertainty. How do you find that? So for any variable, if it is a function of more than one variable, then you find by using partial derivative. For instance, if f is a, it could be like density, so you could say density is a function of measurement of mass and volume. So this is like a partial derivative with respect to density, and then first variable is mass, like here. So this is how you do it, and then whole square, and again the second variable is volume. So again density with respect to volume, uncertainty associated. Now how do you calculate this? You need to calculate this using UB type uncertainty based on resolution that we discussed in our lab. This is what you need to do. So you are measuring the mass, calculate B type uncertainty associated with the mass, calculate volume uncertainty because we know the resolution. So we are doing calculation of B type uncertainty based on only resolution. So you need to calculate this separately, you need to calculate this separately, and then take the partial derivative of this one and do the calculation. So this density uncertainty calculation you require in lab 1 as well. And another for lab 1, you have viscosity is equals to multiplication coefficient and dilating. So again here viscosity we are not measuring directly, it is a function of these two variables. So you could do the same thing for calculating the viscosity and what is the uncertainty associated with the viscosity. So again you are calculating B type uncertainty associated with the viscosity measurement based on this formula. So this is the general formula for propagation of uncertainty. So I'm doing so this is very relevant to lab 1 as well. So for instance, we are trying to measure the density and we want to find the propagation of error uncertainty, because density we are not measuring directly. Density is equal to mass per volume. So here density is a function of mass and volume, okay, two variables. So that is the reason why we are not measuring this directly. We are measuring mass and volume, and you are getting density, but there is error associated with this one, this. So this all propagates to density. So so that's why you have to use the propagation of error analysis. Okay, so for this one again, in this case the uncertainty associated with the mass is already given, but for in our lab resolution is given. Okay, resolution is given. So if you know the resolution, divide by square root 12, so this should give you um plus minus. So this is how you calculate. For volume the same thing, uncertainty associated with the volume is plus minus resolution of whatever the container you have, square root of 12. So this should give you the uncertainty associated with the volume measurement. Okay, So we know this one, okay, and then um, so this is the formula which you have. Always write the formula, find the partial derivative density with respect to mass. If you do that, this is what you get. um, be careful about the unit, it has to be consistent. And then for volume with respect to mass, this is what you get. Put the value, this is what you get. Now we know everything, put it into this equation, so you are getting the the um, the uncertainty due to propagation of error. The key thing is, like, you should understand when to use the propagation error and when not to use it for any variables. If you are not directly measuring but getting from other variable which you are measuring, or in other words like density, you aren't measuring directly but we are getting from mass and volume measurement. So whatever the error here propagates to here, it is a function of two or more variables, so that is why in this case you have to use propagation of error. Okay, so this is how you calculate the uncertainty associated with the propagation of error. So you could do the same thing for viscosity measurement and also the density measurement. So in our lab case, so mass, you have plus minus resolution whatever, and then you have volume plus minus, so you need to calculate the uncertainty associated with that. So this may be related to the resolution, and then get the density uncertainty. And also you have kinematic and dynamic viscosity. Be careful about the units. Make sure you know the relationship between kinematic and dynamic viscosity, and how to convert those as well. That is important for lab 1. So with that, I think you should be able to do the calculation which is based on propagation of error. You could do for volume as well. This is another example. If you want to calculate maybe volume of the cylinder, you have a cylinder, okay. um, Now volume you don't get directly if you calculate the radius maybe with the vernier caliper, so there is some error associated with the that, and also you measure the height, there is error associated with that. Now so volume is a function of R and H. Now find the error associated due to propagation of error, because here we are using propagation of error because volume is a function of these measured values R and H. As you measure R with the vernier caliper, height with the vernier caliper, there is error associated with that, and you will propagate to volume and use the partial derivative formula to find out how much is that error associated. So that's about it. If you have any question, please let me know. Thank you. You can just go through it, it should be okay. This is for the presentation result in relation to our lab.